I want to do is before we jump into domains 5 and 6, I want to do a little review. So I'm going to put some up there. These are all going to fall in domains 2, 3, or 4. I want you to draw the crappy Lewis structure. Then I want you to try to redraw it if you have to with the correct molecular geometry. I want you to give me the name of the geometry, and I want you to give me the bond angle of that molecular geometry as well. So here we go. All right. I want you to try these 5. Again, you know, most people, when they're first starting out, till you really get that VSEPR sheet memorized, we're going to talk about how much of that you got to memorize for Tuesday's test. But most people got to add up the electrons, draw a bad Lewis structure, then redraw it as a good molecular geometry. So give these a shot. We got 5 of them up here. It's going to take you a solid chunk of time. Maybe what we'll do is I'll give you a little bit of time. I'll go over 1, 2, and 3. Then I'll give you some more time to do 4 and 5. Let's do that. So take a couple minutes, 1, 2, and 3. Okay, 1, 2, and 3. All right, let's check in here on 1, 2, and 3. So that's 3 plus 21 is 24. Boron in the middle, 3 fluorines. Boron is happy with 6 electrons, one of the exceptions from last time. So it's totally cool with that. Used up 6, got 18. That's perfect. Oops. That's 120 degrees, and it's trigonal planar. Hopefully you got that. So did you draw it right with the 120 degrees? All right, let's take a look at this guy. 1 plus 4 plus 5 is 10. Carbon in the middle. Hydrogen can never be in the middle. Got 6 left. 2, 4, 6. It's a double. Uh-oh. So what do? You got to add a triple bond, folks. And this molecule is linear. That central carbon atom is in domain 2, 2 bonding groups, no lone pair. It's got a bond angle of 180 degrees, and it is linear. Taking a look at this guy, we got 5 plus 21 is 26. We got a phosphorus in the middle, 3 chlorines coming off of it. Used up 6, got 20 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But now, there's no way we drew this right. So how should this molecule be drawn? Well, it is in domain 4, 3 bonding groups, 1 lone pair. That's domain 4, 1 lone pair. I didn't even see Odera there. Dang. This is domain 4, 1 lone pair. So domain 4, 1 lone pair is a trigonal pyramid, right? So if we take a look at our VSEPR sheet, domain 4, 1 lone pair, trigonal pyramid. So how do we draw that? Well, this is going to require wedges and dashes. So we're going to put a chlorine in the, for trigonal pyramid, we like to put the lone pair in the plane with one of the bonding groups. Then one of the bonding groups is coming out at you, and one is going away from you. So this is a trigonal pyramid. It's going to have bond angles of less than 109.5 degrees. Let me show you what that looks like. It looks like this. So you have your tetrahedral shape, right? You got your thing with 4 things coming off of it. One of the chlorines is in the plane. One of the chlorines is in the plane and 1 lone pair at the top. Then you got one guy coming out at you and another guy going away from you. So the wedge, right, and the dash. Wedge and the dash. Now, Okay, why is the bond angle less than 109.5? Because the whole point of VSEPR theory is that lone pairs take up more space than bonds. So this lone pair up here takes those bonds and smashes them down, right? And we go from that perfect 109.5 of a tetrahedron to now less than 109.5. Cool, keep on trucking, folks. Try CBR4 and OF2. Try to do those, try to draw them correctly with the right molecular geometry. Give me the name and the angle. All right, you got 32 electrons. We're going to put 4 bromines coming off of that carbon, and maybe at first you draw it something like that. And that uses up 8, leaves you with 24. Carbon's happy. Each bromine needs 6 more. It's going to work out if you're a thinker. But we're in domain 4 no lone pairs. In domain 4 no lone pairs, if you look at that VSEPR sheet, it's tetrahedral. So we got to draw it with the 3-dimensionality, right? It actually looks like this. So carbon in the middle, and I'm going to erase these this stuff over here. So carbon in the middle, bromine, bromine, bromine coming out at you, bromine going away from you, and then 3 lone pairs on each bromine. And this has got a perfect 109.5 degree bond angle. Cool. OF2, we got 6 plus 14 equals 20. We're going to do an oxygen in the middle. We got 4 electrons used up. Got 16 left. 2, 4, 6, 8, 10, 12, 14, 16. Perfect. Here's the problem. Once again, we're in domain 4. This is domain 4, 1, 2, 3, 4 things, and 2 lone pairs. Domain 4, 2 lone pairs. That is bent. Now, the nice thing is you don't have to show wedges and dashes for lone pairs. So we can orient this molecule. If I remove 2 bonding groups from a tetrahedron, we could take this molecule and now we can spin it so that the atoms are in the plane and a lone pair would be coming out at you and one would be going away from you. Okay, so coming out at you, going away from you. So you don't have to show 3-dimensionality on lone pairs. You can just put them there like that. This is going to be our bent molecular geometry. And, oh, I didn't do tetrahedral for this guy. So sorry. I said it, didn't write it. This will be our bent molecular geometry. And this is much, much less than 109.5. Why is it much, much less than 109.5? Well, the whole point of VSEPR theory is that lone pairs take up more space than bonds. So these lone pairs are taking up way more space. They're taking these bonds and they are really smashing them down. So they're not just smashing them down, they're really smashing them down. This bond angle now is much, much less than 109.5. So I'm hoping that domains 2, 3, and 4, you got a decent feel for, right? Does anybody have any questions on the VSEPR geometry sheet, which I'll share for domains 2, 3, and 4?
I do.
What's up?
So for number 5, you didn't put the like the 3D like dashes and the triangle for the 2 lone pairs. Did you need to do that or no?
So if you look at the VSEPR sheet, great question. If you look at the VSEPR sheet, we do not show, like, even if you look here, they're using a line to connect their lone pairs. We don't do that. We just put the dots right on the atom. So because we don't do that, you don't need to show the wedges and dashes on lone pairs. So if the wedge or dash is on a lone pair, like when we get down here to T-shaped, you don't have to show that. Just put the, in fact, don't, I'd prefer if you didn't. This paper is just doing that to like show, hey, it's showing a little more detail, right? But you don't have to do that. If you would, I mean, that'd be fine. I mean, I'm not gonna mark it wrong. Like if you know, and that's okay, but I don't even personally do that.